Okay. All right. Everyone can hear me okay? Two minutes. Man, it's been rush hour. Let's see. Let's do this. Oh, all right, 9:40. Let's get started. Lord, thank you for bringing us together this evening. Thank you for everything that you do for us. Thank you for the previous weekend. Pray that everybody is recharged, is ready to go for the week. Help us to stay focused and to get it done. In your name we pray. Amen. All right. All righty. So what are we thinking? What are we doing today? Stuff. I don't know. Nobody really knows, right? If some of the rate my professor in EOX can be believed, right? Dr. D is just learning this as we go along anyway. So there's really no way of knowing what we're going to do except that I inherited these PowerPoint slides, right? Here we go. So we'll recap, talk about Laplace transforms again, right? Kind of continue with this discussion in specific, right? We'll get talking about properties and theorems, and then inverse Laplace transforms today. That's the idea, at least. Let's see how far we get, but I think it's doable. Matrices. So I'm guessing state space, right? State space matrices. I'm going to try to do this on the board here and hope that everybody can see it. I will stop sharing for a sec and we'll see what happens. Okay. So can everybody, first of all, what does it say on the board right now? One sec. Let's try this one more time.
If you're asking us, no idea because you were
perfect. Because it says, can you read this?
200.
and nobody can read it.
P.
So we're gonna have to figure that out. All right, so I'm gonna draw some stuff on. Give me a second. I'll add a new slide in here, and we'll do it that way because that's gonna be the easiest way for this to happen. Yeah. Oh, really? Is that better? All right. I'm going to add another slide and then we'll do this. So perfect. Okay. Get back to Zoom, right? All right. So we'll come back to this in a second. So, right, when we're talking about state space matrices, right? We are trying to fulfill the state equation, which tells us that x dot is equal to ax plus bu, and y is equal to cx plus du, right? This, well, let's use a different color, and this, right, x and u are the same, right? They are the same across these equations. What we are trying to do is we're trying to determine, right, we're trying to determine what is going to happen to this system in a future state based off of what we know has already happened. Typically, the reason that we choose the state variables that we do is because they give us some indication about how energy is transferred inside of our system, right? That's why we typically pick for a mechanical system x and x dot, right? Why? Because that's typically how we store our energy, right? We're either storing it by position or we're storing it by velocity, okay? Okay, x dot is just the time derivative of my state vector, right? Of my x. So if I have x1, x2, x3, then I get x dot 1, x dot 2, x dot 3, right? So what are we trying to do, right? In essence, we want to create, well, let's not even leave it this, let's leave it this way, right? Some generic equation for x dot that is a function of nothing but my state variables and my inputs. This is what we're trying to make. And we have n of these, right? How many do we have? Well, what is the order of my system? That's how many I'm going to have, right? Because I need n state variables. Second order system, I'm going to have 2, right? And typically, what we'll see is we'll get something like, x dot 1 is equal to x2, and then, x dot 2 is equal to 1 over m u1 minus k over m x1 minus b over m x2, right? That's just a generic example, because why am I doing this? Because if people are having issues with the matrices, I'm going to assume that we are okay with getting state variable equations, since that wasn't on the list on there, okay? And if you can get the state variable equations, right? Well, what if I rewrote this instead like this? Right? Is that my camera keeps popping in and out? Excellent. That's what we want. Good thing you don't need to see me to see the screen. Fantastic. Good thing I wasn't using the lecture. Okay, right. So everybody, we have some second order system. It's a second order mechanical system. This is what we end up with, right? We've got x dot 1 is equal to x2, right? Because we've defined that x1 is equal to, well, let's say it this way. The position is equal to x1. So, like this is rounding. My state variable is equal to the position. X dot 1 is equal to the velocity. X2 is equal to the velocity. And X dot 2 is just the acceleration, right? This is where this is coming from. It's just a generic second order system example. So I want to make the state matrices for this, right? I want the A matrix. Well, if I write it out like this, and I change this equation to be this, right? Well, I'm just trying to make x1, x dot 1 and x dot 2 is equal to my A matrix times x1, x2, right? My state vector, plus my B matrix. And in this case, I only have one input, right? So we'll just call it U1 by itself. All right. So how do we figure out what's inside of it? Well, look at that x dot 1 equation, right? So I've got 0 times x1 plus 1 times x2 plus 0 times u1. I'm just recreating this equation that I have here, right? And I'm going to put a green little brackets around this because I want you guys to look at this, right? Everything on this top row associates with the x dot 1 equation. Okay? Everything else is down here, right? So to get x dot 2, I need negative k over m times x1 minus b over m times x2, 1 over m u1. Because remember, right? Remember, when you are doing the matrix operations here, we're just creating linear combinations. What does that mean? Remember, matrices, row times column, right? First row here, 0 times x1 plus 1 times x2. Well, that's going to return me just x2, right? Plus 0 times u1, which is 0 as well. So I just get x dot 1 is equal to x2. The lower one, right? X dot 1 is equal to negative k over m plus negative k over m times x1 plus negative b over m times x2 plus 1 over m times u1, right? We're there again. The output equation is a little bit different because for the output equation, we need to define what y is, right? And y is our output. So what are we interested in measuring? That is what we need to figure out with y. And typically, you'll see in the problems, like in the homework and on the coming exam, if you're told to measure a certain quantity, then that's what you should be using for y. Okay? Now, is that right? Is it wrong? Can you pick whatever you want? Yes, you can pick whatever you want. But in the context of grading your work, I like to know, I'm trying to point you towards something so that everybody is kind of going towards the same answer so I don't have to grade 500 million things. Okay. And I think we've seen through examples, right, that you can use anything, right? You can use x1 minus x2. That was in the train example that we did in class, right? You can use momentum. You can use anything that you want, any linear quantity that you want as an output, anything that you're interested in measuring. So for this case, right, let's just assume for a second that we are interested in measuring the position. We call it Z1. Well, that's just going to be equal to x1, right? Because we, again, look at our equation here, right? Y is equal to cx plus du. We need everything as a function of my state variables and my input. So y is just going to be x1 here, right? And if y is x1 and I only have 1, this would say that y1 is equal to c times x1, x2, right? Because that's x, plus d times u1. Right? So let's see. Well, it is x1. There's no x2, right? Because this is the same as writing this. There's no u, and that's it. That's my output equation for this. Right? So with the matrices, write your state variable equations, write them in order of your x1, x2, x3, right, of all of your state variables. And then you should just be able to pull those coefficients off and throw them right into the matrix, right? Because remember, and if you go back and watch the lecture from when we first talked about state space, right? The lecture from when we first talked about state space. Give me 1 second, I'm gonna add one more slide here. We go back and we watch that, right? What did it tell us about this A matrix, right? Mhm. Sorry. Right? For an n by n matrix, right? For an nth order matrix, an nth order system, right? I will have this, right? Times x1, x2, x3, all the way to x to the n, right? This matrix is A, right? Where does this come from? Right? If I gave you a state space matrix, right, you should be able to get the equation back out, right? Well, in this case, we'd have A11, x1, plus A12, x2, plus A13, x3, all the way out to A1n, xn, right? That's just for that. So look, this is just the first part of my state variable equation, right? And again, if you write it nicely, which I don't always write it nicely, admittedly, but if you take the time to line it up in order of, ascending state variable, right? Then it's just dropping it into the matrix, right? Because this coefficient is just that. Okay. Okay. Is that a little bit more helpful with state space matrices and how to develop the matrices, right? Mike Screech. Yeah, there was a Mike Screech. I remember that. I fixed it, so it's good. We're good. We got it. Laplace. We're gonna keep going with Laplace stuff. Need to come to office hours. Sure, sure. I don't know if you guys saw on Discord. Unfortunately, today I have a meeting. Uh, just right smack in the middle of office hours. So office hours got canceled today. I apologize. They're still on for tomorrow and Friday. And they won't get changed. Or let me know, right, if another time, if you want to meet at a different time, and I can see what I can make happen. Right? I need an adult. Bad news. Most of you guys are, I'm going to make an assumption here. All of you guys are over 18, so you are the adult, right? You are the adult. Now, if you're looking for me to be the adult, then that's bad news. I'm a very poor choice of an adult. Very poor. Just ask my wife. She gets very frustrated. All right, anyway. You guys have any other questions, comments? Is there anything else you want to bring up before? We're going to get into Laplace transforms again. So don't, if you feel like I'm not sure what I'm doing with them, though, that's because we only talked about them for about a quarter of class last time, right? We're going to get into it more, right? So there's that. So you guys have anything else you want to bring up now? No. Scott, the way that you're sitting in front of your background makes that look like you got a poof of white hair coming out of the top of your hat. Um, Very nice. All right.
Just ready for snow season.
All right. Cool. Well, we're gonna keep going. If you're still feel like state space is not something that you're wrapping your head around, right? Please come on, guys. I posted solutions of the homework yesterday. I bombarded you guys with announcements yesterday in LabPod, right? There's a lot of stuff. We had homework 4 solutions, homework 5 got posted, the week 10 announcements for GCU, the parameters for the lab, which we'll talk about in a minute anyway, but they're posted too. There's a lot of stuff up there. All right, let's watch this video.
This video was sponsored by Brilliant. Here we have a mass on a spring. If I pull it back and release, one of 4 things is going to happen. First is completely sinusoidal motion, as in it will oscillate back and forth forever, which will happen if there's no air resistance or damping present. 2 is exponential decay. This happens if we put in some thick or viscous fluid, which will cause the mass to exponentially decay to equilibrium without overshooting. Yes, this entire video will assume damping force is a multiple of velocity. 3 is a combination of the first 2, which happens when the damping isn't as strong.
I knew that was going to happen. Apologize. When I go back.
This video was sponsored by Brilliant. Here we have a mass on a spring. If I pull it back and release, 3 is a combination of the first 2, which happens when the damping isn't as strong or the spring itself is stronger. In this case, the spring will oscillate but still decay in the process until it eventually settles. And 4, literally anything else can happen if we have some input force or just non-ideal conditions. We're not directly as concerned with this 4th case in this video, but we will have inputs later. The main emphasis though is these 3 functions, which is really 2, while the 3rd is just a combination. Now if I had to summarize what the Laplace transform visually tells us in just a few seconds, it'd be this. While the Fourier transform tells us which frequencies or sinusoids are present in a function, the Laplace transform tells us which sinusoids and exponentials are present in a function. In fact, we're soon going to see that the Fourier transform is just a slice of the Laplace transform. Now, here's the Fourier transform equation. It takes in some function of time and outputs a function of omega that tells you which sinusoids are present in your signal. If you put in a pure cosine curve, then out comes a function with 1 spike, since your original curve was 1 sinusoid. Well, for real functions, these are symmetric about the y-axis, so you'll actually see 2 spikes. And the x-coordinates will match the angular frequency of the original signal. If you put in a non-periodic function, you'll get out something more complex, which tells us that it takes infinitely many sinusoids to make up this function on the right. This animation does a great job at showing the original function being a sum of all of those sinusoids, infinitely many, where the sum is seen in yellow, while the magnitude of the Fourier transform tells us relatively how strong each of those sinusoids is for any given frequency. One thing to note is that the y-intercept of the Fourier transform is the area under the curve of the original. Remember, this is the output when omega equals 0. And when omega equals 0, then this term goes to 1, and we have just the integral of the original function, aka the area under the curve. Now for a lot of this video, I'll be working with this equation or something similar, because it has a sinusoid and exponential component. However, we will assume it's 0 for all negative values of t, and it essentially turns on at time equals 0, which avoids the function diverging to infinity. So when we put it into the Fourier transform, out comes a complex function that I won't graph quite yet. I'm not worried about the calculus in this video, but if you just know integration by parts, you can do this, just treat I as a constant. Anyways, I'll FOIL the bottom here to get a new equation just with a separated real and imaginary component, and this is what we'll work with. This function only has one input, omega, so that can just go on a number line. But out of the function will come a complex number with a real and imaginary component, so we need 2 dimensions to represent that. So let's put in some values now. If omega equals 1, then the output becomes 1 over 1 plus 2i, but that can also be rewritten as 0.2 minus 0.4i, which will be plotted on the real and imaginary axis respectively for omega equals 1. Now this is a distance of roughly 0.45 from the origin, known as the magnitude, and that we can plot against the input at omega equals 1. This will be the magnitude of the Fourier transform. Now for omega equals 2 as the input, we get out 1 over negative 2 plus 4i, which simplifies to negative 0.1 minus 0.2i, and that will also go on the output graph. The magnitude for this is roughly 0.224, and that will also go on the magnitude plot for omega equals 2. And lastly, I'll plug in omega equals 0, which outputs just 0.5, no imaginary component, and that will also go on the magnitude plot. Remember, that 0.5 is just the area under the curve of our original function. Well, accounting for the fact that areas below the x-axis are negative. If I were to plot all the magnitudes for any input omega, we'd get this, the magnitude of the Fourier transform. Keep this plot in mind because it will show up soon, but now let's get to the Laplace transform so you can see just how similar it is to what we've done so far. So here we have the Fourier transform again, and this is the Laplace transform, nearly identical. This could also be negative infinity like above, by the way, but especially in engineering, we usually deal with signals that, like I said earlier, turn on at time equals 0, so we can analyze the transient response from there. The only other difference though is we have an s here instead of an I omega. But s is really alpha plus I omega, which I'll substitute in, because now we can separate that exponent into two terms. Now look at this. The Fourier transform of something is found by multiplying that function by e to the minus I omega t and integrating. Well, in the Laplace transform, we have the integral of something times e to the minus I omega t. Meaning the Laplace transform of some function is just the Fourier transform of that function times an exponential term. Doing this for all values of alpha, all real numbers, gives you the entire Laplace transform. To see what I mean by this, let's look at the Laplace transform of the same function as earlier, which again I'm not going to derive. But it's nearly identical to the Fourier transform. The only difference is s represents a complex number, which means the input will require two dimensions, one for the real and one for the imaginary component. The output, just like before, will be complex, so we need 4 dimensions for the Laplace transform in total. But notice that when alpha is 0, we get the exact same outputs as the Fourier transform. As in, this alpha equals 0 line, or the imaginary axis of the Laplace transform, is the Fourier transform. Another way to see this is with the integral, because when alpha equals 0, the exponential goes to 1, and we're left with the original Fourier transform equation. So if I plug in something on that axis, we should get the same magnitudes as before. Like if we put in 0 for alpha and 0 for omega, which goes here on the input, then out comes 0.5, that area under the curve, which goes here on the output. And since I don't really have another dimension, I'll just write that magnitude above the corresponding input. If I plug in 1 for omega and 0 for alpha, which is also on the same axis, then out comes the 0.2 minus 0.4i from before, which on the output has a magnitude of roughly 0.45. And I won't show it, but if I did plug in this point where omega equals 2, the output would have a magnitude of about 0.224. If I was using a third dimension to plot those magnitudes, then we'd see the exact same function as before above that imaginary axis. We could also make a contour plot though. Like just imagine looking down on this graph where colors are assigned to different y values, because then those colors can represent the magnitudes. Then if I move the green line over to, let's say, alpha equals negative 0.5, the outputs will be the Fourier transform of something slightly different. Let me just put the original Laplace equation back up top, and you'll note that since there's already a negative sign here, when I plug in negative 0.5 for alpha, this will just calculate the Fourier transform of our original function times e to the positive 0.5t. That Fourier transform will look like this. And again, I could write the magnitudes to show the outputs, or I could use colors. If alpha is swept through the plane, we get the entire Laplace transform plot. And if we actually use a third dimension for those magnitudes, it would look like this. This plane here shown in green, which I'll fade the plot a little so you can see, is all the inputs s. X represents alpha, and y is really I omega. The 3D plot itself is the magnitude of the complex outputs. This is the Laplace transform of the original function e to the minus t sine of t. The thing is, this doesn't tell us much just by looking at it. So what I'm going to do is graph the equation alpha or x equals 0 that'll give us a plane as shown. Because remember, from before, the alpha equals 0 line actually yields the Fourier transform of the original function, which we can see with the intersecting curve. This is what I meant by the Fourier transform is a slice of the Laplace transform. But now I'm going to decrease alpha while also plotting the original function times e to the minus alpha t. Right now alpha is 0, so that exponential is just 1. But as I sweep alpha, we start to see both plots change. And what you're seeing with that intersection on the right is the Fourier transform of the plot on the left at any given time. Like here, I'll posit alpha equals negative 0.5 because this is what we just saw a minute ago, where the original curve times e to the positive 0.5 t, because that double negative, has a Fourier transform with those two small peaks. Then I'll extend the range of z because as we get closer to alpha equals negative 1, we get an intersection with two much higher and narrower peaks where rendering also isn't looking so good. But anyways, this happens because the left plot is approaching just a regular sinusoid since the exponentials are about to cancel once we get to alpha equals negative 1. And we saw before that a pure sinusoid has a Fourier transform of two infinite spikes, which we can also see on the 3D plot. So the quick summary to what we've seen already is that to construct a Laplace transform, take whatever function you want to work with, multiply by e to the minus alpha t for some alpha, let's just change it to something random like negative 0.93, and graph the 2D Fourier transform of that function. Then keep doing that as you sweep through all values of alpha, stacking two-dimensional Fourier plots side by side until you get your 3D Laplace transform. You will likely not be shown this in a classroom setting, and that's because most of it pretty much doesn't matter. All we care about are these two peaks which do go to infinity, known as the poles. Now if we go back to the 2D plot, those poles are located at negative 1 plus and minus I, which we can represent with an x. Poles and also zeros, which doesn't apply to our function, are pretty much all you'll ever see for these plots. The reason the poles are there though is because if we plug in negative 1 plus or minus I into the Laplace equation, we get 1 over 0, which I'll just write as infinity, because on the plots those are represented with an x. And one more thing you'll notice, when I was sweeping the alpha plane, I stopped at those poles, or alpha equals negative 1, and never went behind that. That's because once alpha goes below negative 1, the function we were plotting diverges, which means the Fourier transform of this does as well. So the Laplace transform doesn't actually exist in that region, whereas this is the good region which we give a name to, the region of convergence. Just think of this region as all the alphas such that this part of the Laplace transform eventually converges to 0. This means everything I said earlier with taking the Fourier transform of this function and that being a slice of our plot is true if that slice is in the region of convergence. This part is, so we're good there. However, this part is not, which is why again the function diverges for those alpha values. Essentially, this exponential term has now 1, making Laplace undefined in that region. Anyways, going back, notice that for our pole, the imaginary coordinate is 1 and negative 1, which matches the coefficient or angular frequency of our sinusoid. The real component of negative 1 matches the coefficient in the exponential term. This is finally what the Laplace transform visually tells us. The imaginary axis represents the sinusoids, and if my poles are on that axis, it means my original function is just sinusoidal, and the further from the origin the poles are, the higher frequency that signal is. If my poles are on the real axis, then there are only exponentials in the original signal, which decay faster as we move further from the origin. When the pole has real and imaginary components like here, then we have a combination. Since this graph is symmetric about the real axis, I'm going to move it down, and to help with visualizations, I'm going to change the x-axis so every tick mark is 0.2 units apart. But anyways, now the pole represents this function with that exponential and sinusoidal component whose graph looks like this. If I move the pole away from the x-axis, then the sinusoidal frequency increases, causing faster oscillations, and the resulting equation will have an angular frequency that matches what we see on the imaginary axis. If I move to the left, then the number in the exponent gets more negative, causing for a faster decay rate. The equation for this function still has coefficients that match what we see on the axes. And if I move to the right, then the decay rate slows until we reach the imaginary axis where we get a pure sinusoid. And poles on the right hand side correspond to functions with exponential growth. So now Laplace transform equations should make way more sense. Like sine of 3t has the Laplace transform of 3 over s squared plus 9. If we find the poles or when the denominator is 0, we get plus and minus 3i, and this tells us the original function has no exponential term, but it does have a sinusoid with an angular frequency of 3, which we already knew. However, the most common talking point you hear with Laplace is not anything we've seen so far, but rather its ability to turn calculus into algebra. If we take some arbitrary function x of t, it will have a corresponding Laplace transform x of s. But if you take the derivative of that same function, the Laplace transform will be the exact same thing times s. There is an extra term that has to do with initial conditions, but I will assume those are 0 from here on. Then the Laplace transform of the second derivative is again the same x of s times s squared this time. And some more initial condition terms that we'll ignore. This pattern would continue, and this is where Laplace is really useful. For example, this is the differential equation that describes a mass on a spring. We've got the force from the spring itself, the damping force, which is a multiple of velocity, some arbitrary input x of t, and all forces summed to mass times acceleration here. The grouping of the terms just came from some rearranging. So what we can do is take the Laplace transform of both sides. However, due to linearity, this is the same as taking the Laplace transform of each individual term. The transform of some x of t is x of s, and for k times some y of t, it becomes k y of s. For by prime, from the rule above, we get out the same y of s times s, and the b is there as well. Then the second derivative outputs ms squared y of s. Since all the terms on the left have a y of s, I can factor that out to get this here. Some of you may know this part as the auxiliary or characteristic equation. We'll then isolate y of s and we're left with this here. So we may not know the actual output y of t, but like we've already seen, if I know when the denominator of the Laplace transform is 0, aka the poles, then I can tell you a lot about your output function. Let's assume the input is a constant force because this is the same as having a vertical spring where the mass is subject to gravity. Like good engineers will say the mass is 1, thus force is 10 newtons. And when the block is released at t equals 0, or the force is immediately turned on, so to speak, this is known as a step function written u of t, and its Laplace transform is 1 over s. Meaning our force, 10 u of t, becomes 10 over s, which we'll plug in for x of s. Then again, mass is 1, and let's say the damping coefficient is 0, while the spring constant is 1. Then I'll just move the s down to the denominator. Since there's no damping, the spring will oscillate forever around in equilibrium, but let's check that this is shown with our Laplace equation as well. We have one pole at positive I and another at negative I, which is what makes this part 0. Then we also have a pole at 0 from the s out here, and we'll put everything on the pole 0 plot. Again, I'm hiding the bottom to make room, but it always looks identical to the top half. And now we have everything we need. These poles say that the output will have a sinusoid with an angular frequency of 1, and we haven't seen a pole at the origin yet. But remember, this is the area under the curve, the intercept of the Fourier transform. The pole thus represents an infinite area, which just means there's some offset in our output, or something that doesn't converge to 0 to get that infinite area. Since we're considering the top to be y equals 0, then the output is exactly what we expected. If I increase the value of k or make the spring stronger, then the poles start to separate more and more, which represents faster oscillations about in equilibrium. If I were to add some damping now or increase b, then we expect slow exponential decay. I'll just stop here at b equals 2 for example, so we can see there's now a sinusoidal and exponential component to our equation, which matches what was expected, even though no, I'm not graphing the exact output. If we make the damping much stronger, we get to a point of critical damping, where finally oscillations go away and it's only exponential decay. Then moving from there, the exponential decay just slows down from this term not decaying as fast. Plotting the path those poles just took is the idea behind a root locus plot, by the way, for those in the controls class. But this is where the design part comes in, because by analyzing the locations of the poles, we can determine how a system will respond to different inputs. Many systems out there would be extremely difficult to solve using only functions of time. Plenty of you probably know how not fun this would be to solve using only differential equations. But moving to the S domain makes it an algebra problem that's much more doable. And especially in control systems, Laplace is crucial. I mean, we just did a problem where an input was multiplied by the system's transfer function and we got the output transform. It wasn't that bad. But even when there's more going on between the input and output, it simplifies fairly nicely when using the S domain, as we can still just multiply the input by a more complex but still manageable transfer function to find the corresponding output. Of course, there's plenty more to all this, and if you want to continue your learning, I highly recommend checking out Brilliant's series on differential equations. This includes 2 full courses which start the basics for those who may.
Yeah, we don't need that. We're good. All right, so that was a long video with a lot in it about Laplace transforms, right? Hopefully, for those of you who, so personally, I find the animations of what happens when poles move around nice, right? Because you get to see what happens to the system. We understand a little bit more what is happening when we're in different areas of the S-plane, right? The real and imaginary axes. And we're gonna get to some of those properties today, right? There you saw now. Yeah, should have crossed this one out, right? That one was due. We're good. Remember, lab 2, right? Lab 2 due this this Sunday, right? Lab 2, the video is on YouTube. Dr. D and Professor Price do labs, episode 2. It's got some sweet music in it if you haven't watched it already. Anyway, yeah, there's also an announcement giving you some stuff. We've got homework 5 due on the 22nd, and then our exam. Right? So here's the deal with the lab, right? So many systems are a combination of 2 or more subsystems. These hybrid systems are very common in our day-to-day lives. In this assignment, students will develop a mathematical model for the rotational electromechanical system. So you're probably not going to be able to see it super great. I'm going to try anyway, because it's up here in the front. Yes. Close your eyes, everybody who's at home. Right. And shut off, right? Perfect. Let me get it in position now. All right, so this is the system, right? I know you can probably hardly see it. There is the video online that will hopefully aid you in getting a feel for it. If you're in class, you come up and check it out after class, that's fine, right? You've got 3 sleds, they're attached to a motor, right? You give it some current, the motor spins, you move, right? Okay. Also, probably should have used the left-handed screw on that because it loses itself every time that you run it. But anyway, all right, so that's the general idea. So what do you need to model, right? Well, you've been given all of the coefficients that you need, right? And you've been given the motor output curve, right? That gives you a nice linear relationship between torque and motor speed, right? Which, as it turns out, is going to be the same as your motor constant. Okay. Make sure you're checking units though when you're doing these things. Okay. So you need to create a mathematical model for this system. If you're thinking to yourself, that looks a lot like that train problem that you had us do in class last week, that's probably a really good place for you to start. Okay. You need to model this in Simulink, and you're going to give it an impulse, right? Not an impulse, but an input, right? So you model it in Simulink, you give it an input, and you're going to check what you're trying to measure is the final the displacement of this final part, okay? At a specific current value that you can do. You can work in teams of 2 to 3. Only one person needs to submit. Yeah, they can simulate model. So new mathematical model by hand. They can simulate model based off the mathematical model. Test the results of the simulated model to what you got out from watching the video. So yes, this is another one where you have to watch the video and figure out what the final displacement of this part is. Right? Eyeball it. Don't have to go frame by frame. And like, just get the average. What is the average final displacement of this third part? I request the person that changes the masses on these these cards themselves are roughly around 200 grams, 200 grams. So the cards, the weights, the masses sorry. The weights that you were given, the masses you were given in the video, not include that extra 200 grams. So just heads up. All right. Do you have any questions on the lab? Right. Remember, sources of error. That's a big thing. Right. What are some sources of error? Remember, human error. Don't say that. All error is human. To err is human, but to forgive divine. Right. That is the saying. So, human error. Be specific. Right. If something's not working, we need to understand why it's not working, and we need to come up with ideas for how we can get it to work. Okay. All right, you guys have questions? You guys have any questions so far? Anything on the lab? All right. Please don't wait until Sunday to start it. I feel like that would be a horrible idea. And you should probably start it before then. I would probably start taking a look at it yesterday. But if you didn't start today, take a look at it, see if you have any questions, and then ask them in office hours tomorrow since today is okay. Right. When it says validate the model using the system, right, you're going to essentially say, what is the percent difference between what your model tells you the displacement of the final part is versus what is the displacement you got out from your model, right? Or from the actual device itself. Don't want people to get sick. So okay. Questions? No? Okay. Here's the parameters in case you didn't see them. I think the one that I didn't put on LoudCloud is the J, right? J. And that's the J that is here. And this right here. Sure. No questions right now. Okay. I know Zach was looking for it yesterday. I hadn't updated it. It's updated now. Especially the one in Discord, right? But we've got Life Livers, Dr. Desanitizers, and Zoom Engineers in first through third. 65.5 to 61.5. Uncalibrated calipers in the bags. Yikes. Static waffles. SDCK. Michael Scott Paper Company. 185.31. Doctors Without Doctorates. Warzone. Stormlords. Zero Division. Matilda 20 Compass. And Wizard. Soon you're going to get an opportunity to wager some of these points in a Final Jeopardy type. Well, it's basically Final Jeopardy. Like, I'll ask you a Jeopardy question, and you and your groups can talk about it, and then you submit an answer, and you at the end of class, like on a Thursday. So, not this week, probably not next week, since is next. All right, but we'll figure it out. All right, Laplace transform. So we already did one when we left, right? On Thursday, we finished class with the Laplace transform. Now, I know you probably can't read it behind me, but this is the definition of a Laplace transform, right? And the definition of a Laplace transform tells us that if I want to take the Laplace transform of some function of time, this is the integral from 0 to infinity of that function of time times e to the negative st dt. The video used alpha. We're going to use s. It doesn't matter. The same. Okay. So you guys find the Laplace transform of A. We'll take, I'll give you guys 15 minutes. Find the Laplace transform of A. Hint, use the definition that I just wrote up there on how to find the Laplace transform of A.
Dr. D,
Yes.
is the S always negative?
Yep.
Okay.
When you're doing the definition of e to the negative st, it's always e to the negative. Yeah.
Okay, thank you.
How's everybody doing?
Dr. D, I have a question about the
Sure.
table that you gave us. Did you purposely not put in for the functions of S when this is like the Laplace transfer
Yeah.
pair?
Yeah, Carl, I left it, it's blank on purpose.
Okay, just,
It's blank on purpose. You guys are gonna have to fill it out this week.
oh, okay, this. Thank you.
Mhm. I think 5 more minutes. 5 more minutes. I really want you guys to work through this. Oh, one more minute. One more minute. Yes. All right. That's time. All right, that's time. Time's up. All right. Okay, so I don't know if you guys were watching chat or not, but how do we handle this, right? Well, is A a function of time here? No, right? F of t is a function of time, but A is just A, right? Will always be A. It is just a constant. And because it's a constant, we can pull that out in front of our integrand, right? And so that's what we'll do. We'll pull that out, and then we'll just left with e to the negative st dt. If you take the integral of that, right, and some of the conversation I was having, right, what is the derivative of e to the negative st? Right? If it helps you think about it, instead of using the variable, what's the derivative of e to the negative 2t? Negative 2t. What is it? So that's the integral, right? 100%. Yeah. Right. You take the coefficient down, right? Put it in front, and then you're just left with e to the negative st, right? So negative, that would be the derivative. So if we want the integral, how do we integrate that and get back to e to the negative st, right? Well, the integral must be the antiderivative in that case. Right? And the antiderivative would be, for this, negative 1 over s times e to the negative st. So, right, that brings us to the end of the first line that I wrote there. So I've got a times negative 1 over s times e to the negative st, and I'm going to evaluate that between 0 and infinity. Now remember from Thursday's class and from calculus, right, because that hopefully wasn't the first time we've ever heard of improper integrals, but you can't really evaluate something at infinity. What you're really doing is you're taking the limit of this quantity as time approaches infinity, right, on the high end. And if we do that, it says e to the negative infinity, but it's really as e approaches negative infinity. And there's another way of writing something to power like this, right, is the same as writing that, right? And so as e gets, as this number right here in the denominator, right, as s gets larger and larger and larger, it's going to drive this fraction to become smaller and smaller and smaller, right? And so as this approaches infinity, this term goes to 0. And so we're left with negative 1, right, negative 1 over s times e the zero. Either the zero is just one. Did I not put a? I didn't carry a negative sign here. This should be that should be false, right? Because it's minus a negative. Yeah. Because we do infinity, evaluate at infinity minus evaluate at zero, but we should be evaluating negative 1 over s. Yes. Okay. Sorry about that sign error. But then we're left with a over s. What is a over s? What is this? Why is this significant?
I don't know if I was supposed to do this, but like I would just remember from the tables, even though you hadn't revealed, that when you have a constant, in this case it was a, it's usually like, but if it was 1, the f of s usually becomes 1 over s when s is greater than 0 at all times.
Right.
So I thought that's what we were just.
Right. So if you were given the table, right, you would just use the 1 over s, but it's for any constant, right? This is the more general form. If you remember the example from Thursday's class, right? The example from Thursday's class, we did a e to the negative at. That's the same as a times e to the 0, right? So if a is 0 in that, we're left with a over s. But what's important about it is what Danny said, right? It is an integrator. But another way of thinking about it is it's the step function. 1 over s is what the step function looks like in Laplace, right? So 1 over s is what a unit step looks like. A times 1 over s would give us any step function that we want, right? And that's why this is important, because remember from the video we watched at the beginning of class, what we're eventually going to do is we're going to take our system model, we're going to take the Laplace transform of the output side, and we're going to take the Laplace transform of our input, right? And so if you're told that you have a step input, right, you're going to end up with something over s as the Laplace transform. Now, do you always have to derive these as is? No, right? That's why the Laplace transform tables exist. Turns out that no matter how many times you take the Laplace transform of a, it will always be a over s, right? So now we know that, and we move on, right? We use the Laplace transform table. Like I said, on the exam, you will be given a Laplace transform table, right, to use. So don't worry, don't feel like you need to like memorize all those. That's fine. Right? And you have one that you're going to fill in for your use on like homework something, right? Okay, so big thing though, right? Big thing. All right, we're going to talk about some properties, and these properties are pretty important for everything. But let's move to this. Next slide, please. Thank you. So in a similar fashion, we can compute the Laplace transforms for other common time functions, right? For steps, sinusoids, damped sinusoids, right? And they're all tabulated here, right? And so you can see, third entry in this particular Laplace transform table is A, right? Which gives us A over S. The unit step is 1 over S. Unit impulse is just 1, right? Unit ramp, we've got them all, right? This one corresponds to example 8.1 from your textbook, because I lifted this from the textbook, and you know, we didn't do 8.1, but we could. Okay. So part of it is understanding how to use the tables, but the real thing, the real utility of this has yet to be shown, right? Because taking the Laplace transform is great, but the real money is getting it back out after you've made it a Laplace transform, right? As it says in the video, using algebra to solve differential equations, right? That's what we want to do, because differential equations are great, but algebra is better. So how do we do this in MATLAB? Can we do this in MATLAB? And sure we can, right? You need this symbolic toolbox, right? So you type, right? So there's that, right? So we're going to take the Laplace transform of 3 sine of 2t, All right. So we say sims t, that defines our time t as the symbolic variable, right? Then we say, well, f is equal to 3 times sine of 2 times t, right? So defines our function sine of 3 times sine of 2t as our symbolic object. Right. Then we're going to say, well, capital F is the Laplace of lowercase f. So Laplace, right? All lowercase Laplace, that's the command, right? And then we're going to use pretty, because pretty is going to make it look nice. Okay. What if you don't use pretty? Well, it's fine. You don't have to. If you use pretty, you'll get what you see here on the screen, which is this nice typeset mathematics look. Okay. If you don't use pretty, you're not gonna. It's not gonna look like this, but you'll still get the answer. So let's see. Let's not check. Sine some constant times the sine of 2t. Right. Go back to our table. Right. So sine of omega t. So this should be a times sine of omega t. Right. Omega for us was 2. And we should get out omega, so 2 over s squared plus 2 squared. That's what we should get. Whole thing multiplied by 3, right? Because there's a constant. Hey, look at that. 3 times 2 on the top, right? Divided by s squared plus 2 squared. Look, it checked out with our table. This is my surprise case. This is my surprise case. Turns out there are things on the internet that can be believed. Right? Turns out. Okay, so you can check all your Laplace transforms if you do them by hand, right? If it's something that doesn't automatically match up with the table, right, you can do it by hand. Okay? But the amount of time that you'll run across something in the wild, right, that doesn't match up with what's in your table is pretty slim. The tables are pretty extensive. The one that you have to do is not very extensive. Right? It's a snapshot of the most common ones that we'll use. But if you go on Google and type in Laplace transform table, you'll be inundated with results. So we can talk a little bit about poles and zeros. Okay. We know poles. We've heard poles before. Poles are the roots of my characteristic equation. Right? Notice how it's set up here, right? I've got f of s. My Laplace transform of s is equal to some numerator divided by the denominator, right? The numerator is some constant times these sets of factored portions, right? And the denominator is these factored portions of some characteristic equation. So the values of s is equal to negative z1, negative z2, all the way to negative z sub m. This makes our Laplace transform equal to 0, right? If anything in the numerator, right, if we make any of those equal to 0, right, then the whole thing's equal to 0, and we call those the zeros of our function. The zeros of our Laplace transform. We're not going to go over why zeros are important, because that's a different class, but we're going to understand what they are. Likewise, right, we went over this in that video a little bit, but the poles are the areas in our function that cause this to go to infinity, right? So contrary to popular belief that has been spread around by one of the professors who no longer works here, right? Professor Voldemort, you can't divide by 0. It's not a thing. Well, you can, but the problem is that everything can be divided. It can be put into groups of 0 infinitely many times, right? That's what it is. So if you get the roots of the characteristic equation, these are our poles. What do the poles equate to? Like it said in the video, when you get 1 over infinity, you're going to get these large spikes in the Laplace domain, right? And that's what the poles are. That's what the poles are. So in this simple example here, right, I have the Laplace transform f1 of f. That's equal to 1 over s plus 3. So I don't have any zeros, right? I don't have any zeros. How do I know I don't have any zeros? I don't have any s terms in the numerator. So there's no zeros, but I do have one pole, that s is equal to -3. Turns out that that's the root of my characteristic equation as well, right? What's the time constant of such a function? Time constant, right? So think about that. Remember, we had 1 over s plus 3. So I run it back up to here. I look, right? Look at my Laplace transform table. Okay, 1 over s plus a is a constant. So 1 over s plus 3. So I should get e to the -3t, right? And that's what I get down to. Now, if I end up with e to the -3t, what is the time constant of this function? It was like a week ago. How do I find the time constant? One minus 1 over e. So you're close, Danny. You're close, right? Or we find the time to make this e to the -1. How much time? What does t have to be to make this e to the -1? Yes, 1/3. So tau is 1/3 here. Is it seconds, hours, days? I don't know. I wasn't given that much information. All I was given was the Laplace transform. Yeah. Okay. So what's the point, right? Why do we care? For this class, we're not going to see very many zeros. In fact, most of our functions that we have developed so far have no zeros, right? And that's fine. Where poles and zeros really come into play is when we start talking about control systems, right? And we're not going to do that here. But we do need to understand that the natural dynamics, right? The natural dynamics of our system, or the open loop nature of our system, is dependent on our poles, right? It's dependent on the root of our characteristic equation. And that's what's important to remember. So let's jump into some properties, right? So
Wait, I still have a question. So wait, the time constant, did we just say that we're just going to say that it, for this case, it's 1/3? Or are we saying like t equals like 1 over s or something? Do you get what I mean? Is like that the official equation for this type of thing, or is it like just in this scenario?
Well, in general, the time constant is always the amount of time that it takes for you to get e to the -1, right?
Okay.
So another way of thinking about this is, right, we know that our root is -3, right? And if you take the inverse of the absolute value of your roots, that's going to be the time constant. Right? So the time constant is always 1 over your root. Right? It will never be negative, but it's 1 over the absolute value of your roots. Okay? So if you have more than one root, you could potentially have more than one time constant, right? If you have a complex conjugate root, it's 1 over the real portion. Right? Because remember, the real portion of our roots defines the exponential behavior, and the imaginary portion defines the sinusoidal behavior. Okay. Any other questions? Okay. So, property. There are certain things that, all right, so in some of these they went over in the video, right? So So now we're going to talk about them in earnest and hopefully deal with it, right? So it's important to remember that the Laplace transform is a linear operator, right? And that means that it behaves linearly, right? Now, what does that mean? Well, we can apply the superposition properties to this, right? Because it has linearity. Specifically, right, if I take the Laplace transform of some constant times a function of time, the answer, right, the Laplace transform will become that constant times the Laplace transform of whatever the function is, right? And we've seen that. We saw that on the last one, right? You can pull the constant outside of the integral, right? All right, so this one's a nice one too. If I take the Laplace transform of a times some function f1 of t plus another constant times f2 of t, this is the same as taking the Laplace transform of each of these individually, right? What this is really doing is this is saying, well, L of A1 times F1 of t plus L of A2 plus F2, and that's no plus, A2, F2 of t. So you can distribute the Laplace transform across different functions, right? You can distribute the Laplace transform to the different parts of this function. And then look what happens. If you did it that way, now this just follows that first property that we laid out up top, right? So if you know what the function is, you can go into the Laplace transform table and adjust the function. And if you're just being multiplied by a constant, then you just multiply whatever you found in the Laplace transform table by that constant. Okay. Superposition allows for us to add multiple inputs together. We talked about superposition last week when we talked about how to make some of these more complicated input responses, right? Where if you, specifically in Simulink, if you want a pulse, right, you can add two steps together, right? Or subtract one step from another. That's superposition as well. Okay. So far, anybody have any questions, right? So if you have a constant, you can pull the constant out of the Laplace transform, right? And I've proven that based off of the definition where we take the integral. Property B, I can distribute my Laplace transform to as many functions as I have adding together. This is going to be an important property for us in conjunction with the ones for differentiation that we're about to talk about. Okay. So what about differentiation? Well, we went over this in the video. The derivative, the Laplace transform of the derivative of a function is equal to S times the Laplace transform of the function minus the initial condition. Now in the video, we assumed a zero initial condition. That will not always be the case. That will not always be the case. So in its general form, right, you need to have an initial condition in order to do this. What if I take the Laplace transform of the second derivative? If you take the Laplace transform of the second derivative, you'll get s squared times f of s, right? So s squared times the Laplace transform of that function f of t minus s times the initial condition minus the initial condition of the first derivative, right? So just like when we're doing differential equations, when we have a second order system, we need two initial conditions and so on and so forth, right? And this will stack. the further that we go. Now for this class, S squared is fine, right, for everything that we're going to be doing. But if you had something really gross, right, S to the n, right, you would just continue with this format, right? You have S to the n times the Laplace transform, and then you start subtracting initial conditions, right? And your first initial condition for the base condition, right, would be S to the n minus 1, then S to the n minus 2 times f dot of 0, all the way down to f to the n minus 1 times 0. Are we okay with the differentiation thing? The differentiation and property B, right? These three properties, B under superposition and A and B under differentiation, those are going to be really important, right? Only like these are the ones that we are going to use over and over and over again. Right? These are the ones. We want to know these. We want to know these. They get simplified greatly when we talk about transfer functions, which we won't talk about today. That'll be the next class. Okay. Does anybody have any questions about differentiation or superposition? I want you to notice something. If you differentiate this, right, and you've got this second order derivative, right, what have you done? You've added an s squared term in here, right? So we'll see why that's important with an example a little bit later.
Wait, just to confirm, the blue is if we came across it like that with a, is that a U? For the, is that U2 or is that
Carl, this is
A2?
all real A's.
Oh, okay, my
No,
bad. I didn't mean to.
And I
You just split it up. Okay.
to both parts. All right, so you can, it's totally fine to distribute your, if you're going to take the Laplace transform of the big thing, that's the same as taking the Laplace transform of each part of that big thing. Yeah, big thing is the technical term that the mathematicians use. I didn't make that up. All right. Cool. Any other questions? No? These are the important ones, right? I'm telling you, we're going to see them a lot. A lot. All right, so what about integration? All right. So if you're going to integrate, if you're going to take the Laplace transform of the integral of something between 0 and some time t, it's just 1 over s times the Laplace transform of f of s. Okay. So this one's important, but honestly less so than the derivative ones. But it's important to understand that multiplying something by 1 over s gives you the effect of taking the derivative of, or taking the integral of it, right? What if I have multiplication? I have some function and I multiply it by e to the negative a t. Right, so I'm going to take the Laplace transform of some function of time times e to the negative a t. Well, this becomes the Laplace transform of your function at s plus a. Another way of thinking about this is, right, remember what the integral, right, remember the definition of a Laplace transform, right? Will give us this, right? And so these things would combine to that, right? Not as common, right? Not as common. Honestly, for what we were doing in this class, right, the ones that I circled in red or boxed off in red on the previous slide are infinitely more important. 100%. All right. You guys have any questions on these? You guys good? No. Okay. There's no questions. So there are a couple more properties that, well, I guess these are theorems, really, they're not properties. We can talk about the final value theorem, right? And so what if I want to take the limit of a function as time goes to infinity, right? How does that affect the Laplace transform? Well, the limit of a function of time as time goes to infinity is equivalent to the limit of s times the Laplace transform as s goes to 0. Now I want you guys to remember this. It seems good. Good. My slide messed up. I'm really excited about that too. Very, very nice. I want you guys to think about this, right? When we have been we've been dabbling, right, in transfer functions in the time domain. Yeah? The answer is yes, we have. Okay. So if we good, that should do it. So what do we when we talk about DC gain, right? When we talk about DC gain, what were we doing? DC gain is just us finding the final value of the system, right? As time goes to infinity, right? As time goes to infinity, this was the same as us having capital D be 0, right? Because as time increases, we will reach steady state. And as we get to steady state, then all of our differential terms go away. Now, in the Laplace domain, S, multiplying something by S is like taking the derivative of it, right? And so as the limit as S goes to 0 is going to get us to steady state, right? And that is going to give us the final value of our function, right? Because once we hit steady state, we'd say that that goes forever, right? All right, so we can use this to compute steady state value. So if you know f of t, right, you have a big complicated function that you don't really know how am I going to find steady state of this. Well, take the Laplace transform and multiply it by s and take the limit as s goes to 0. We'll do an example on it. It only holds true when our system actually reaches steady state. All right, so shockingly, if your system doesn't reach steady state, then the final value theorem, which may still yield an answer for something that does not reach steady state, may still, right? We need to, so we still need to check the roots, right? Make sure you're always checking the roots to understand what's happening with your function. What type of, are you expecting something to be stable or unstable, right? Because if it's unstable, you're not going to reach steady state. And if you don't reach steady state, there's no final value, right? So make sure you're checking that. Right, so for example, the final value theorem does not hold for a sinusoidal function, right? Yes. So that might be true, but does that mean that we don't hit steady state with a sinusoidal function? The answer to that is no, it doesn't mean that. We'll talk about what steady state looks like for a sine wave when we get the frequency response. But for right now, right, there's no ascertainable steady state, right? Okay. So that's final value theorem, right? And this one is important because if you can do this, you can find the DC gain of the system, right? You can find what my system is supposed to be at steady state. We also have the initial value theorem. So we want to find out what happened right after we give this input, right? At time 0 plus. It's like we get the input and then we take the slice of the system right after our input goes live, right? Well, it turns out that if you want f of 0 plus, you take the limit of s times your Laplace transform as s approaches infinity. As s approaches infinity. So we can use the Laplace transform to get the initial value of our system. There are some homework problems where you got to use final value and initial value. There are some homework problems where you're going to want to use it. All right, so that's the properties in the theorem. Do you guys have any questions so far? Doing all right. Okay. The people at home have been awful quiet today. Well, actually, no, not so much as other days. I'd say probably higher, more participation than ever from at home. You guys still doing okay? You have any questions?
Doing pretty good.
All right.
I think just seeing some examples, trying to work through them.
Yeah, the example definitely helped.
No examples. The rest
Well, I
of
meant, yeah, is that's why I was.
not doing any more the rest of the semester.
Oh,
I'm
will rip us.
fine. Ask and you shall receive, Carl. Ask and you shall receive. All right. So let's find the Laplace transform of this. So how do we do this, right? We know what f of t is, right? We weren't given any initial conditions, which is fine because we don't have any derivatives in here, right? We don't have any derivatives. Are you supposed to do this all by hand? Am I expecting you to do this all by hand? No,
Yes.
use the table. Use the table. Your incomplete table. Go online, type into Google the Laplace transform table, right? You know what? You guys have that up. Did everybody get a chance to copy this down? Yeah? Okay. Well, I'm going to go and I'm going to put this up for you guys so that we can do this. Yeah? There you go. So I want you guys to see it. All right. So take a couple minutes and see what you can piece together from this table and what we know about properties and everything that we've done. Okay. Let me ask you guys a question here. Let me ask you guys a question. You've got this large Laplace transform, or this large function, 0.2 plus 2e to the minus 3t minus 5e to the minus 6t plus 8 sine 4t. All right, you got this thing. If I wanted to take the Laplace transform of f of t, is there a property that would help me here, or do I need to find the row on the table that has all four of these very specific functions combined?
No, you just split them all up.
Right. Like it says on the board that you can't read, the Laplace transform of the big thing is the sum of the Laplace transforms of the little things. Okay? Patent pending. Like my new catchphrase. It's pretty long for a catchphrase. All right. I'll work on it. I'll shop it. I'll shop it for you guys. Okay. All right. So what do I have? I've got 0.2. Is 0.2, what is 0.2? How would you characterize 0.2?
Constant.
It's a constant, right? All right, so that's going to be row 3 here, right? Then I've got 2e to the minus 3t. So that's an exponential, right? The next one's an exponential, right? So we can take the Laplace transform of each of these pieces, right? So if we do that, right, the Laplace transform of a constant from our table is just going to be that constant times 1 over s, plus the Laplace transform of 2 times e to the negative 3t. Well, that's an exponential that's multiplied by 2, and an exponential is s plus 3, right? 2 over s plus 1 over s plus a times 2. Okay, where a is 3. I guess it's s minus a. Right? Anyway. Minus, well, the next one is going to have the same functional form. And then we've got this sine wave, right? And this is 8 times my sine of omega t. And so that's, sine is omega over s squared plus omega squared, right? But omega is 4. And 4 times 8 is 32, divided by s squared plus 16, which is 4 squared. Okay. So if you get a big honking function like this, right, that looks really intimidating because we never did anything like that, but we did all the pieces, right? You can always break it up. Well, you can break it up, right? Whenever you have a linear function that you're trying to take the Laplace transform of, you should be able to apply it to each of the pieces. So, okay. That's not too bad, right? We use our table, right? Break it up into pieces, go into the table, find the corresponding function in the table, and apply your constants as needed, right? Just in case you guys wanted to double check, this is, so you go back to the slide we just showed, this is going to be for A, right? This is going to be e to the negative at. This is also e to the negative at, and this one is sine omega t. Right? That's what we're looking at. Let's I'm using B, C, and D there, right? Why? Because there's different constants in front of all of them. We're just multiplying through by the constant. We're just multiplying through by the constant. Okie doke. Any questions about this one, right? We okay with this one? No, everybody's cool with this, right? Oh. So let's try. Oh, here's where I'm going to tell you about your participation for the week. Okay. Those work that table that Carl was talking about that I posted last week in the announcements. I want you guys to fill it out and send me a PM by the beginning of next class, right? Not during class, but the beginning of next class. Okay. So let's try this, right? We haven't done a final value theorem, right? So let's find the final value theorem if it exists and the initial value theorem, okay? All right, so here's I'm giving a Laplace transform, right? Here it is. 7s plus 3 over s squared plus 2s plus 10. Right, so let's recall that if I want f of infinity, right, this is the same as the limit as s goes to 0 of s times f of s, right? By definition. So this is the limit as s goes to 0. Well, all right, if I multiply by s, I'll end up with 7 times s plus 3 times s over s squared plus 2s plus 10. Right? Okay. So I can multiply through if I want, right? I can make that 7s squared plus 21s, right, if I wanted to. Don't really need to, right? So if I take the limit of this, so I'll take the limit of this function as s goes to 0. If the limit as s goes to 0 gives me 0 on the top and 10 on the bottom, right? Everybody cool with how I got that? So if s approaches 0, right, the top terms go away because we've multiplied everything by an s, and the bottom, the only thing that sticks around is the 10. So guess what? That's our steady state value, 0. We're going to hit 0 at steady state. Can't have that. It's important. All right, so that's final value, right? What about the initial value theorem, right? I want f of 0 plus. Remember, when is 0 plus? 0 plus is like we start at 0 and then infinitesimally a small amount of time later we have 0 plus, right? It is the conceptual time, right? It's saying we've given it just enough time for our input to turn on, and then right after the input turns on, this is what happens, right? This is what happens. So how can we do this? Well, remember, this is just the limit as s goes to infinity of s times f of s. So this is the limit as s approaches infinity of 7s squared plus 21s over s squared plus 2s plus 10. That time I multiplied it out. Right? They're equivalent. If you know s times f of s, you always know s times f of s, right? So we got a problem here, right? Because if I take the limit as s approaches infinity here, I'll get infinity over infinity, which is obviously 1. No, it's not. Don't do that. Right? Which is obviously sad face, right? Because that's probably not good. So how do we handle something that gives us back infinity over infinity? Say that one more time, Dave. Analytic completion, sure. Or we can dig deep, right? I'm pretty sure this is a calc 1 topic. We can dig super deep and invoke the name of our friend L'Hopital. And we use L'Hopital's rule. Right? Okay. What's L'Hopital's rule, Dr. B? I forget. It's a great question, right? L'Hopital's rule says that the limit of something, of some function, is equivalent to the limit of that same thing of its derivative. Paraphrasing. All right, so if I use L'Hopital's rule, right, I'll take the limit as s goes to infinity, right? So L'Hopital rule. And to do this, I'm going to take the derivative of the numerator, 14s plus 21. And I'll take the derivative of the denominator, right? Because L'Hopital's rule says that the limit of something is equivalent to the limit of the derivative of the numerator divided by the derivative of the denominator, right? So what is this saying? This is the change in time, right? The change of these functions with respect to time is going to have the same limit as the original function. And then if we take the limit of this, right, as s goes to infinity, well, that's equally as bad, right? Because we're still left with infinity over infinity. So we'll do it again, right? L'Hopital's rule, LH. So we'll take the derivative of the numerator again and the derivative of the denominator. And in this case, we'll be left with 14 over 2 or 7. And 7 is a smiley face, right? Because 7 is an actual number and infinity over infinity is not. So yes, we have to use L'Hopital's rule, right? And this is going to be pretty common, specifically for initial value theorem problems. So, specific. Okay, time. Perfect. I'm going to give you guys, let me give you guys 10 minutes to do the final value theorem of this. Right? So just calculate the final value theorem. We'll take 10 minutes, we'll talk about it, and then we'll do the initial value theorem thereafter. Right? So just work on the final value theorem, take 10 minutes. Do I expect you guys to remember the final value theorem equation? Please hold while I look at the master sheet to let you know if I expect you to or not. Nope. Hey, guess what? It's on there. Right on there. There it is. That's what we're looking to do. So, all right. Let me say something. We forgot to do one thing on the last problem, right? Should always check the roots first. Make sure you check the roots on this, right? Because final value theorem, if it exists. And so if you check the roots first and it doesn't exist, right? Right? Remember, then you're wasting your time by doing the problem. So checking the roots. All right. Does anybody have roots? What are the roots?
I'm just gonna go out on a limb. 0, -4, and then plus and minus 5i.
Yes. We'll call it J, Carl. Okay. Call it J. All right. So yeah, we've got. All right. So what does that tell us about the response that we would be expecting? What does that tell us? I guess the question is, are you expecting something that is going to reach steady state or not? Right, that becomes the question. What does root of 0 mean for us? What kind of response do you get from a root of 0? Flat. Well, it's right at, all right, so it's at 0 on the real or imaginary thing, right? That's 0 on the real and 0 on, it's a marginally stable group, right? Different. What about -4?
Isn't
Stable.
that unstable?
Yeah, that would be a stable system, right? But -4 is going to give us a time constant of 0.25, right? -4 is an equal to time constant of 0.5. How do I figure that out? Well, remember, this is real, right? And a real root is going to give us this, right? And that means that tau would equal a quarter, because that's the amount of time that it takes me to get to e to the -1.
I can't see what you're writing.
Oh, sorry. There you go. What about plus or minus 5j? What type of root response does a purely what does purely imaginary give us? Oscillatory, right? Harmonic oscillator. And this is the dynamic that is going to persist, right? This is the dominance for the system. How do we know that? Because it doesn't die out. The other response dies out, but you're going to have this oscillatory response that goes on forever. And so we are going to say that it never reaches steady state, so the final value does not exist. Okay. So if the final value doesn't exist, then we're done, right? Check the roots. We see that we have a harmonic oscillator, and then we move on. So now we've got to do our initial value theorem, right? And this one gets kind of ugly. This gets kind of ugly. So I'm going to take the limit as s goes to infinity of s times f of s. All right? We'll do this. What's on? We'll do this one together. I'll do the first part of this with you, and then I'll let you guys do some in next part. So it is. It is, Danny.
So wait, do we have to find an initial value for each root? Or is it there's just one still?
So, Carl, we're going to take s. We're going to multiply this Laplace transform here, right?
Yeah.
Times s. And if we do that, right? So, Danny, you are right. It is, the answer is 3, right? But we're going to prove why it's 3 using the initial value here. Right, so I just multiplied this. I just multiplied this by s, right? And when that happens, these two s's cancel, right? Because I've got s over s in there. That's just going to be 1. So it actually simplifies it a little bit, right? And if I take the limit of this, right, this is going to give me infinity over infinity, right? So I'm going to have to use L'Hopital's rule. Okay. Another way that you can do this, right? So we got to use L'Hopital's rule, right? So let me, just to refresh you guys one more time on L'Hopital's rule, I take the derivative of the top, right? And if I take the derivative of the top, I get 9s squared plus 12s plus 16, or plus 18, sorry. In the denominator, right, give me 3s squared plus 8s plus 25. How did I get that? Well, I multiplied those two together and then I took the derivative. Okay. Well, you get infinity over infinity again, right? Let's do it one more time. So you guys tell me, what do I end up with if I apply L'Hopital's rule here one more time?
No, for future reference, if we're like writing this out and showing like we understand it, would you like us to go every time? Because like if we hadn't canceled, like okay, if we still cancel the S's, we still have to go through L'Hopital's like 3 times. But if we like know that like it's gonna cancel all the S's, can we just take the initial numbers of the highest S and then just show that that's what the numbers values will be? Or would you still us like to write each time?
You know what? To be honest with you, with this, I don't really matter either way, right?
Okay.
You've already taken calculus, right? If you show understanding of doing it, that's fine. What's the reason I'm keep doing it out is because some people might feel a little bit more rusty than others, right? And having the framework is helpful. All right, so if I take L'Hopital's rule one more time here, what do I get? Yep. Thank you, Danny. 18s plus 12 over 6s plus 8. All right. Well, guess what? Let's do it one more time. So we just become a chain of L'Hopital's rule. All right, then this one becomes 18 over 6, which gets us. Okay, great, we got through. And then you guys already got that, and we're good. All right, well, there we go. Okay. You guys have any questions right now? No? Doing okay? Hopefully review. Yeah. Everything sounds familiar. Bunch of French names. All right. Cool. All right, any other questions? Anybody good before we hit the button and we move on? All right. Okay. So we're going to talk a little bit with the remaining time left today about inversion cost spectrums, and obviously we'll pick up where we leave off on Thursday, right? So this is all great, right? This is all great. Everybody, we can do Laplace transforms, right? We've had our calculus review, but this is where the rubber meets the road, so to speak, right? It's great that we can put things into Laplace space. It's great that we can take it from time domain, put it into the complex domain, but we want to pull it back out, right? So to use a very, very weird sci-fi reference, right? So you guys know Nightcrawler from the X-Men, right? So the way that Nightcrawler's teleportation powers work is that he goes into another dimension, travels through that for a little bit, and then comes out someplace else in the world. Now, that power would be garbage if he couldn't ever get back out, okay? So we need to learn how to get back out. We need to learn how to get out what we put into, into the Laplace domain, okay? And how do we do that? With the Laplace the inverse Laplace transform. So what's the goal? Right. Our goal is to take the Laplace transform of a function of our system model and the input. We're going to mess around with it in Laplace space. Then we're going to pull it out in the time domain. Why do we want to do this? Because we can get the solution to our differential equation from doing algebra. Okay? So our overall goal is to use the Laplace transform to obtain the response of a dynamic system that is subjected to initial conditions and or known forcing inputs. Right? How? We're going to use a systematic approach for solving ODEs and obtaining a dynamic response. Right? So we take the Laplace transform of every term in our ODE. We incorporate the initial conditions. We're using the differentiation properties. And then we're using the results from that step. We solve the Laplace transform of the dynamic variable y. And so you might have seen it on the previous slide, and hopefully you remember from Thursday, but this is going to involve one of my top 5 favorite expansions of all time, the partial fractions expansion. Typically in these cases, we're going to end up with partial fractions, right? So we obtain the system dynamic response by taking the inverse Laplace transform, right? So if you have y of s, you're going to take the inverse Laplace transform. What is this going to look like for us? Essentially, we don't have a framework for pulling this back out, right? But what do we have? We have the Laplace transform. And if you know that something term, when you solve it, ends up as 1 over s plus 5, right? Then you know you have e to the minus 5 because I know what the Laplace transform is. And I know what function I need to create that Laplace transform. So I'm literally going to look at my table and say, I have this form in Laplace space. This is the function that needs to be of the same form. Okay? You'll see. Okay. This will probably be the last thing that we end up doing. So imagine I'm given this second order system with initial conditions as follows, right? 2y double dot plus 10y dot plus 12y is equal to u of t, where u of t, or where y of 0 is -1, and y dot of 0 is 0.5. And I want to determine the dynamic response to y of t if u of t is 4 times the unit step. So a step of 4. Okay. So where do we start? Let's start by taking the Laplace transform of just the output. Okay, so I'm going to start by taking the Laplace transform of 2y double dot plus 10y dot plus 12y. Well, we've seen that this is just the same as taking the Laplace transforms of each of these things separate, right? I can take the Laplace transform of those things, right? We just used the superposition rule B, or property B. Now we need to use our differentiation properties, right? These are the properties that I circled or I put in the red box. Okay, so the constant can come out, right? So if I'm looking at L of 2y double dot, this is going to equal 2. Well, what's y double dot? S squared times y of s, right? Minus s times the initial condition, y naught, minus y dot naught. If I plug in my initial conditions, I plug in my initial condition, I'll get 2 times s squared times y of s plus 2s minus 1, right? All I did was I plugged in -1 for y naught, and all right, so if I did that right, this should be positive. -1 for y naught and 0.5 for y dot naught, right? That's all I did, and then I multiplied through by 2 because there was the 2 out in front of everything. That is the Laplace transform of the second derivative of y. Now I can do this again, right? And in this case, I want 10 y dot, right? Well, this is going to be 10 times s times y of s minus y of 0. This is 10 times s y of s plus 1. So this is going to be 10s y of s plus 10. So we've got two parts. Well, Laplace transform of 12y, right? This one, how do we handle this, right? Well, it's just this. The Laplace transform of a function, and this is gonna sound really stupid when I say it, and I understand that fully, okay? But the Laplace transform of the function is the Laplace transform of the function. The Laplace transform of y of t is y of s, right? 12 is the constant. We don't know what the output is. We're trying to figure out what the output is. So we're going to leave it as y of s, okay? And I realize that that sounds confusing, right? And it sounds like it's not helpful. I understand that, but I don't. So the Laplace transform of y of t is y of s. That's capital Y of s. That's what it is. Laplace transform, what isn't 12 a constant? Yes, it is, but I'm multiplying it by y of s, right? We don't know what y of t is. So we're going to leave it in its most general form and just say that the Laplace transform of y of t is equal to y of s. We are going to solve for y, okay? So before we do that, let's look at u of t, okay? Because we also want to take the Laplace transform of u of t, right? Which is 4 times u of t. And u of t is the unit step, right? We know that. The unit step is just equal to 1. And so if you go to your table, right, this is the same as having a, right? Unit step of, or step of 4. So this is just going to be 4 over s. And this is my input, right? Just let's remember, this is the input. Right, so we need to take the Laplace transform of both sides of our input-output equation, okay? We need to take the Laplace transform of both sides of our input-output equation. The unit step is equal to 1. The Laplace transform of 1 is 1 over s. 4 comes out, right, because it's a constant. 4 times 1 over s is 4 over s. Now we have everything that we need. We're going to essentially plug in everything as a Laplace transform. Right? So what is he talking about? Indeed, what is he talking about? Well, remember, the original equation was 2y double dot plus 10y dot plus 12y is equal to u of t. I took the Laplace transform of this entire thing, both sides. The Laplace transform of this equation, given what we just came up with, is 2 s squared y of s plus 2s minus 1, right? That all was the Laplace transform of 2y double dot plus 10s y of s plus 10, right? This all goes to there. Plus 12 y of s is equal to 4 over s times u of s. I forgot to put the u of s in. I apologize. All right, so let's go back. All right, so in the same way that we use y of s is the Laplace transform of y of t, we get u of s here. Right? We can't leave it out. Can't leave it out. All right, so Laplace transform of a constant 4 over s. Laplace transform of u of t is u of s. Right? That's still right. And so that's where we end up with here. Okay, that's what we end up with here. Okay. Combine like terms. Put all your y of s's together, right? So we combine like terms, we'll get 2s squared plus 10s plus 12 whole thing times y of s is equal to 4 over s minus 2s minus 9. Right, so all I did was I took y of s, I left y of s on the left, I moved everything else to the right, okay? Well, that looks gross, so I'm gonna do one more algebraic step here.
What happened to the u of s when you brought over the minus 2 of s minus 9?
Sorry, yeah, that should be borrow. I've got to make this one. I've got to make this one thing, right? I'm going to make this one thing. So I'm going to multiply the entire thing by s over s, right? I'm going to multiply these two things by s over s right here to create common denominator, right? You know what? I think I botched it when I told you about that, but we'll talk about that in a second. Then I solve for y of s. I realize that the u of s is not there. Give me one sec. We'll talk about it. Okay. We end up with this y of s. We'll start here on Thursday. I keep wanting to say Friday, but my brain does not want to admit that we have class on Thursday for some reason. We'll start here. All right, so where did the u of s go, right? Well, Dr. D put a u of s in where he shouldn't have. And none of these u of s's should be there. Why? Because this is u of s. I found the Laplace transform of it. Ugh. I apologize. I know that that probably is going to cause some confusion. So let me say this, right? This is where we're at. Okay, so when we take the Laplace transform of the input, we know that u of t is equal to 4 times u of capital T, which is 4 times 1, right? So remember, whenever we take the input, that u goes away, right? What if we left it as u of s and we never did this? Well, we can talk about transfer functions at a different time, but not today. Okay, so we're here. We have an expression for y of s, but much like Nightcrawler, we are now stranded in the alternate dimension and we don't know how to get out. We're going to get out and we're going to get back to something that looks familiar, okay? Right now, if you try to match this up with the Laplace transform table, you're going to come up at a loss, right? We're going to come up at a loss. So what do we do? Tune in next time, to find out. All right. Move on. I'll put up the thing. Start the poll everywhere. Spoiler alert, partial fractions expense.
Hey, Dr. D,
Yeah,
where's the participation located in LoudCloud?
it's last week announcements, there was a Laplace transform table sheet that I put up in the announcements.
Okay. Thank you, sir.
Dr. D?
Yeah,
So we only have to fill out the blank table, or is there some problems to do too?
no, just for participation, fill out the blank table.
And you want us to write them in, or can it be like a type thing?
You can type it if you want, either way.
Okay,
Yes, if you guys type it in and then submit it, but I mean, if you want to print it, write it, scan it, and submit it, that's fine too.
okay.
I do actually have a question on the participation for the table. It has like its numbers, and I don't know if mine was just when I was just slowly typing stuff in, it might have been wrong, but it says like number like 1, 2, 3, like each of the ones, and it's 7, and then it goes to 10, 11, 14. Like, is that on purpose?
It's because I pulled those from a different table, Carl, and I
Oh,
truncated.
okay. Okay.
Yeah,
I didn't want to do them, and then it's like, oh, you're missing these. So,
No,
but okay then.
It's not like the senior prank where the seniors let pigs 1, 1, and 3 out, and then the administration spends the rest of the day looking for pig number 2. Not that.
Okay then. Thank you.
Looks like
See
we
you
have
on
to
Thursday.
stand for senior prank now. Didn't know you knew about that one, Dr. D.
Yeah.
Thanks, Dr. D.
No problem.
No office hours today, right?
No office hours today. Unfortunately, I had a meeting that I have to get to.
Today was important. All right. See you tomorrow.
All right, sounds good.
Thank you. Bye.
Easy. See you guys. Mhm.